This short video presentation is to show people how to use the Catia program to do a very simple single degree of freedom system dynamically in the Catia program. Now, my analogy of doing these problems in Catia is trying to kill a fly with a cannon, because the program, at least the FEA capabilities within it, is for problems which are a lot more complicated than doing this particular situation. And the motivation behind me doing this is, excuse me, when I was teaching my introductory vibrations course, the students already knew Catia and they had done some finite element calculations in it, except that they could not use it to do their very simple single degree of freedom systems or multi-degree of freedom systems in the software. The main reason is that there was no documentation, meaningful documentation, or tutorials on how to do this. And it's not very straightforward. It's a simple problem, but because it's so simple, it requires quite a few steps to go through in order to be able to achieve it. Now, I'm going to do a series of these type of videos. One of them is starting with this problem where we have a mass spring damper system. It's a single degree of freedom system, obviously. Starting at initial conditions, suddenly it's applied, it's subjected to a constant load. Now, obviously, this is a dynamic problem, okay? So what we're going to do is we'll do it in 3 steps. Once I do this thing, I will come back in the next video and assume that this is subjected to a sinusoidal load. So basically, it's a load that is harmonically changing or sinusoidally changing, and these are very common in rotating unbalance or some base excitation problems. And finally, in the third video, I'm going to come back and do a 2 degree of freedom system where there are 2 masses attached to each other, etc. Now, let's quickly review the solution to this problem. So what we do is in the vibrations course, we show you that, or we show students that the natural frequency, undamped natural frequency is k over m. With that data that I gave you, the natural frequency is going to become 1.414 hertz. Radians per second, or in hertz, it's going to be 0.225. Okay. Hertz. And of course, the time period for the natural vibration, undamped natural vibration, is just the reciprocal of that times 2 pi, or basically 1 over 0.225. Okay. Now, the damping ratio can be calculated through this expression, and the damped natural frequency is right there. So, in that course, or in any vibrations textbook, you're shown that the solution is made of 2 parts. The transient part that's going to die down if there's damping, and there is the homogeneous. There is a particular solution, which in this case is written as the Duhamel integral or the convolution integral. Now, because the initial conditions are assumed to be 0 initial position, 0 initial velocity, the expression for A and B in the transient part is going to come out to be 0 and 0. So this you can drop, and this term you keep, and that's going to be your solution to the vibration problem. Now, in the event that we have an undamped situation, the zeta is 0, and therefore that reduces to this expression. And if you F naught is constant, for example, if you pull it out, we are assuming that it's 10 newtons, so it's going to be 10 over 4, which is 2.5, and then this is a very simple integral that you can do that and work it out. Now, in the event, in the event that there is damping present, well, things you have to do the integration. There's going to be an integration by parts involved, but anyway, if you work it out, do the math, it's going to give us to this number, this function, and notice that as time goes on, this thing actually goes to 0. And the solution approaches the static solution. That's a no-brainer. Now, I also will put down some slides here without actually talking about them, and these are the steps that I'm going to follow in order to do the problem in Catia. In case you want to stop it and go back and see what the steps are, is right here. This is one slide that I'm not going to go through. and this is the second slide. So you can see there's some unexpected things to do which one would not expect it from a very simple problem like that. But anyway, so this is the rationale behind doing this tutorial, because it's not a straightforward problem. So first of all, you can do this thing in part design, but I'd rather do it in the generative shape design. And the reason is that when I do the 2 degree of freedom system, at some point I have to join two lines, and that joining is done in the generative shape design. That being the case, why don't I actually do this problem in there too? Okay. So the spring, we're going to create it by creating two distinct points. One at the 0, 0, 0. The other one is 1 meters away. Now, springs do not have length in practice, and or at least in simulation cases. And but here in Catia, because it's strange, because we're going to need a beam element to be able to solve this simple single degree of freedom system. We still have to do an element, and the element happens to be a beam element, but we're never going to use it. There's certain things you have to do, but you're never going to use it. So here's the situation. Let me start with a point at the global origin right there. Let me put another point, create another point, which is 1 unit away in the y direction, 1 meter away, right there. And then I'm going to create a line between this point and that point. Okay. And I'm going to apply material to this thing. Now remember, we're going to mesh it with beam elements, but we're not going to use these beam elements, but you still have to do that. And we're going to apply material, and you might say, well, why are we applying material? Because it's a mass spring damper system. Where is this material going? Well, since we're going to be using beam elements, we need a material on it to be able to mesh it. So I'm going to put a dummy aluminum material on this, for example, but I will go and change the properties of this dummy material, make the stiffness so low, make the Young's modulus so low that actually it will not interfere with the with the spring stuff that we're going to do later on. So for the Young's modulus for aluminum is 70 gigapascal. It's a big number. So what I'm going to do is I'm going to change this thing to, how about making it 1? And the density for aluminum is 2,710 kilogram per meter cube. So I'm going to make this thing also 1. Basically, you want to make it so small that these will have no effect. This beam will have no effect on our calculation. Okay, good. Now let me save this thing. Now we're going to go to generative structure analysis right there. You see this? Generative structure analysis. Let's do a static analysis first. Make sure that everything that we're doing is going to come out to be correct, at least in the static case, because if this doesn't give you the right answers, then there's no hope in doing the dynamic problem. Static case, okay, good. Now, I'm going to hide these points because I don't want inadvertently to put restraints and load on these later on. So I'm going to hide this. Now, we're going to have to mesh this thing with beam elements. So you have to do that manually. Here is the model manager. Here's the model manager. This is the beam mesher. I'm going to select this. Notice that the element type is linear because this one actually is not implemented in the version of Catia that I have. So it's just a linear element. Now, when you say minimal mesh, it takes this thing, regardless of what number you have here, it takes this thing and divides it into 2 elements. That's one option. Or you can put a 1 meter here. That means there's going to be 1 element from here to there. If minimal mesh does not lead you into some weird, stuff, just go ahead and make this thing 1. Okay. So we say okay. Now we need to specify the cross-sectional property of the beam because this beam by itself, you need to specify some cross-section. So I'm going to go to 1D property and circular cylindrical beam, okay, with the radius of, I'll make it 0.1 so that it's tiny here, it doesn't block your view. And for this is fine. And I'm going to select, these are totally irrelevant. The Young's modulus, the Young modulus of the aluminum, the density of the aluminum, the cross-section here that you can see, these are totally irrelevant to the calculation. They should not influence. This definitely will not. But that Young's modulus and density also, you have to put a small number so it won't. Now, if this is bothering you, you can always hide it, or you can make the radius smaller, but it doesn't bother me, so just close it. Because it's cylindrical, you don't need an orientation point, and that takes care of it. Now, I need to create a general analysis connection, because this is where we do our real stuff meaning create our spring element. You click on the general analysis, not general analysis connection. For the first component, you select this end, and for the second component, you select the other end where the mass is going to go later on. Okay, so this is a connection that we have created, and it's right there. You can see that. Now I click on this user-defined distant connection property. Now this happens to be in the toolbar, which is called distant connection property, but the one that you want user-defined. Now there are different ways of doing it. You can do it with rigid spring. There are all these options that you've got. I was able to, well, I used both of these rigid spring, and rigid spring, they both work. There's no problem. Or spring and rigid, I bet that also works. So here, let's say I use the rigid spring rigid. You select this, and you click on the wrench here, because this is where you specify the stiffness of your spring. Let me remind you that the stiffness of the spring was 4 newtons per meter. So here I put a type 4 newtons per meter in the translational stiffness in the direction y. Okay, this is global, right? This is global. The global direction is y. That's how my beam is oriented. And we say okay. And then select the support. Now the support is, you can't select anything here except for this connection that you created. See that? You can select a connection, but you cannot select anything else. You select a connection, and then you can close it. Our spring has been created. Okay, good. Now, let us go and clamp that end. So we're going to go to clamp this end, like, and we apply a static load of 10 newtons. So if you look at the problem that we're doing, the problem is dynamic later on, but we're going to assume that this is applied very slowly. Therefore, it's a static problem. So you apply distributed force on that point in the direction y. Direction y is like that, 10 newton. And if you look at it closely, you see that actually the force has been applied to that. Now, if I solve this problem for deflection, I better get 2.5 meters. Okay, because deflection is going to be F naught over the stiffness. That's that F naught over K is going to be 2.5 meters. I better get that, otherwise there's something wrong. So let me save the analysis. So file, save management, analysis, save as. I'm going to call it white noise, just so that I remember what these things are. Later on, I'm going to apply white noise to this as a dynamic problem. Okay, very good. Let's say okay. All right, let's run it. Compute. Not a big deal. There's only a single element there. Oh, well, let's look at the deflection, but there's something that I want to do, which I neglected, and that is to put restraint in order to make sure that this point moves along the direction y. I wanted to apply user-defined restraint. I forgot, although this may work, but let's check it out. Where is that? Deflection and 2.48 meters. Okay. Now, if you go and make those Young's modulus and things like that perhaps smaller, you're going to get closer to 2.5. Now, but one thing I want to do is I want to actually deactivate this plot, deactivate this, and I want to apply a restraint here so that it only moves in the direction x, direction y. And the reason I want to do this thing is that I want to take away all those extra degrees of freedom which causes this thing to kind of bend and actually is okay, but rotate and things like that. So I'm going to apply user-defined right there, user-defined. And on that point, I'm going to say just move in the direction y. It's not going to make much of a difference when you run it. You're going to get exactly the same number as before, but it will take away some of those frequencies that may be popping out when we do the dynamic case. So if you look at this, double click, and you can see that nothing changed, and you get 2.48. It's just that this is not going to go out of plane in any direction, and that's why the frequencies are going to be limited, and that's what you really want. Single degree of freedom system, only one frequency that we are interested in. Now, we're going to say insert frequency case. Now, for restraint, I'm going to use the same restraint that I have in my static situation. So I'm going to say reference, and the reference is the restraint from the static case. You can see that right there. I selected this. Otherwise, I would have to go and specify restraints at this point, which I don't want to do that. So it has been created. Now, the only thing is that if you double click on this, you said that it says 10 frequencies. Now, I don't have 10 frequencies. I have only one frequency, or depending on what I did, maybe one or two. If I say 10, it's going to come back and say, I don't have 10 for you to calculate. As a matter of fact, let me keep it as 10 and show you that it's going to come back and say, hey, I don't even have 10 frequencies. So what are you doing? That's fine. Now, we want to also put a mass here. Okay, remember, this is a single degree of freedom system, mass dampers system. So where is the mass? So we go here. There are different ways you can do this thing. The very first one is what we want is basically the support is that point, and the mass is 2 kilograms. I put a 2 here, and that's because right there, the mass was 2 kilograms, right? Don't worry about this damper right now. We'll worry about it later on. We say, okay, all right. And we're going to have to run. It's going to come back and say, hey, I don't have 10 frequencies right there. So let's say it says degree of freedom is 1. So let's go ahead and change this thing to 1 and run it again. Nothing fancy is going to happen. If you look at the displacement, okay, if I click on displacement and double click on this, basically double click on that deformed shape, occurrence, here's a frequency, the only frequency 0.225 hertz, which is exactly what we got here. Good. Now, that takes care of finding the natural frequency of a single degree of freedom system. What you want to do now is to go and say, okay, first of all, let me deactivate this. Now, what you want to do is to say, okay, I'm going to make this thing a dynamic problem. Now, in other words, a transient dynamic problem. So insert, we already did the static, we just did the frequency. You go all the way at the end, it says transient dynamic response. You click on it, it says, okay, where is your frequency case? Well, this is the one that you just did. Notice that in the reference, you need the frequencies, and I did it. It's right there, right there. You click on it, and then it says it's a load excitation. Yes, it's a load excitation, and we say, okay. Good. Now, one thing we need to do here, and this is often something that people forget, is that I have to tell the software that this force that I'm going to be applying is constant for all t's. That's what Catia calls white noise. The value of the force is a constant value for all time values. And this is what Catia called white noise. So first thing you have to do is to go and select the white noise modulation. If you look at the modulation toolbar, there's a modulation toolbar. It's kind of hard to miss this thing. You see there's a straight line here, and over here there's a time modulation, frequency modulation. You've got two choices. You can use the white modulation, or you can use the time modulation and put an Excel spreadsheet where the first column is time, the second column is 1, 1, 1, 1, 1, 1, which means it's constant. Okay, so I'm going to use the white noise. Okay, in the next tutorial, when I do the frequency time modulation, I will create an Excel spreadsheet, and we're going to have to import that, etc. So here, time modulation. You click on it, not time modulation, white noise. Click on it. Nothing is going to happen. You can give this thing a name, but if you look at your tree, you will see that in the tree, this has been created, and it says white noise right there. Okay, so now we're going to go to transient dynamics that we already inserted. Double click on the load, double click on the load excitation, double click on this. It says, okay, where is your load? Well, the load is coming from that static load that we applied right there. See that? This was in the static case. This was in the static case. We applied a load of 10 Newton. We select this, and it says, okay, where's your modulation? The modulation is the one that I created, white noise. Uh, uh, or if you had, for example, an Excel spreadsheet, you import it here, as we will do in the next tutorial, you select that one. But this is fine. White noise is fine. This is a factor that you can take whatever load that you had here, which was 10, and you multiply it by that, okay? Now, I don't want to do that because 10 was already correct. 10 Newton was already what I was supposed to have right there. In the load, 10 was already correct. I don't have to scale it up, etc. So we say, okay. Now, if you put the cursor here, I'm going to do several of these. Put the cursor on the slide. You don't have to run anything. Everything is already done. Okay. Right click, display to the generate 2D display. You click on it. Okay. So you say next, just one graph and finish. This thing pops up and it says, okay, you want to plot something. Okay, so remember, we are after displacement of that tip as a function of time. So we want to plot something. It says, okay, go and select a node. And this is the reason that we actually created that dummy beam elements, because we want to be able to go and select it. So if I minimize this window, don't close it, just make sure minimize this plot. You can go back there and select that node. In principle, you should be able to do it. Now, if you can't select it, let's try it. Let's try hiding a few things. Let's try hiding a bunch of things here. There. That is the node. Okay, it happens to be node 1, by the way. There's only 2 nodes here. 1 element, 2 nodes. 1, 2. Okay, so that's the one. We say add, and we close. And if you click on this 2D plot that we generated, we're going to get this. Okay. Now, you might say, okay, first of all, how did it know that you had to go to 10? Let me close this, okay? And let me close that. If you double click on the transient dynamics, it tells you what is the time that you want to go from time of 0 to time of 10. No, let's say I want to go to time of 20, okay? And then how many steps? The more you have here, the less jagged your graph is going to be. So let's make it 200. And you say, okay. And then once again, you double click on this. See, it's a lot smoother. Let me minimize this for a second. Okay, now let's check this out. So this goes from time of 0 to times of 20. Okay, and the amplitude goes to the amplitude is 2.5. It should be. Just look at your analytical solution. Just look at your analytical solution. It goes like this, around 2.5 static solution. So 0, 2.5, up, 2.5 down. And so the reason it started at 0 because the initial condition were given as 0 and 0. And we are generated this thing, which is exactly that curve. Now, by the way, notice that the frequency is where is that? The natural frequency is about 4.4. You might say, wait a minute, this is 4.4, so natural period is going like that. So this gives you, this is 4. Hang in there. Wait a minute. Before I do that, this thing is fine. There's nothing wrong with it, except that I wanted to show this is the amplitude. Right click. Let's try a few things here. Let me close that. Right click, limit, format real. Okay, so that's fine. It didn't make any difference here because of the nature of the problem. But in the event, yeah. So the other thing that you might say, wait a minute, what about that damping? Notice, by the way, that the amplitude is decreasing. Just look at it. The amplitude is decreasing. So is this a damp problem? And if so, where did I actually specify the damping? Here's the situation. Let me close this thing one more time. If you double click on damping, there's the damping line. See that? So if it's a modal damping, you click on the wrench. By default, it took a 1% damping. Now my case is actually not 1%. It is 17% right there. Okay, this is my solution. And that's why if you run the problem with 17%, it dies very quickly. But what I want to show you is this. What I want to show you is that what if I don't want to include damping? Well, no problem. So you go here and you say damping 0. You say okay. Okay, so we put a 0 for global ratio. We close this thing and close that and double click on this thing again. You see, no longer it's damped. You can see that before the amplitude was decreasing, and it was 1%. By default, it took 1%, and I didn't mind. My situation is not 1%; it's 17%. But what I did, I made that 1% to 0, and now you can see that this is actually that that solution. You can see that. Okay. Yeah, and by the way, the period, you can see that this is the period for about four and a half seconds. Now, if you want to actually change the damping to what it's supposed to be, 17.6, right? Look here, 17. What is that? 17.6. This means it's 0.17 multiplied by 100, 17.6. So you go there. Let me minimize this. Double click on the damping. Click on the wrench, make this 17.6. Then we say okay. Okay. And now double click on this again. And there we are. Right there. And this is that plot which matches the analytical solution. Okay. So what I have done for you is did the problem as a static problem, inserted frequencies, inserted transient dynamics, and showed you how to get the graph of the displacement as a function of time. And there's a whole whack of things here that you can do, which I'm not. You can try it on your own and see how good it's going to go. So yes, single degree of freedom system, we can do it very quickly, at least for the case of it. Constant force, suddenly applied force. I'm going to show you in the next tutorial. I start from the very beginning, so there is going to be an overlap between static solution, frequency case, and then when it gets to modulation or transient dynamics, I have to create an Excel spreadsheet, which is not going to be a constant value of the force. It changes with time. Good luck, and let's stop this.